My name is Krishna and I work as Watson and cloud developer with IBM. So my primary areas of interest are Internet of Things and machine learning, right? So and my current obsession is something called GANs or machine learning, that is generative adversarial networks. If you'd like to talk or chat about that, we could meet offline and do that, right? So before we proceed into whatever we are trying to do here, right, I'd like to just understand how many of you heard the word machine learning before? I know, stupid question, right? It's okay. So how many of you are currently trying to build something on the machine learning? I mean, it's a buzzword, everyone wants it on their resume, right? Okay, very few, right? The rest I assume are mostly senior and architecture developers and other stuff, right? So basically, I have, here what we are trying to do is, today we'll see a very small story of how data has been evolving and the hardware that is supporting it and building and pumping all of the infrastructure that we see every day is evolving with it as well, right? So so let's quickly jump in. So the first thing that we know, before the good old days wherein you had nothing but you don't even have computers, electricity was as good as the latest invention, and in those days what happened was everything we had was information, right? So can someone give me a brief description of what information is and what data is? How are they different? Any ideas? Yes, right. So basically, when you're looking at it, right, a processed data is called information. Or if you go the other way, information is something that is needed, and data is something that is, a collation of all that is needed, right? So in olden days, if there's something that is written down or something that is coming out from someone, it's mostly information, because people used to only give out things that they need, and those are the good analog days, right? But with the digitalization came a new headache, that is, the data is everywhere. Everyone's trying to put something out, but that's not what I need, right? So there are changes in the way that we started consuming data, right? So the information became scarce and the amount of data became increasing, right? So when there's more data, and the only way to get information from data is actually to crunch that data and process it back into information. So for those days, that's when a new machine or something that's new came into existence, called the computers, right? That's when you started these things, these boxes started collecting information, they crunched it for us and started giving out us data and the forms that we need them, right? So that's when data came in. But what happened is, somewhere some idiot just thought, why can't computers start learning and doing stuff on their own, right? He just thought, wouldn't it be good if computers can think like humans and act like them as well, right? That's when, back in some late 1950s, was this first term called machine learning coined, right? That's when you're actually seeing computers to start understanding data in ways better than the original ways, in ways that are unprocessed, or in our words, unstructured or semi-structured, right? That's when machine learning came in. But the primary hurdle is, back then there is only limited amount of data, and also the processing powers of these things. If you think back, the computer that powered Apollo mission was as powerful as today's calculators or your smartphones. It's so teeny compared to what we are doing right now. So that remained the primary constraint, and that is like a ball chain for machine learning to take off, right? So that's when what happened was, there's this other revolution, something that happened after 1970s, that is called the internet, right? So basically, when you have a bundle of computers, everyone is now capable of owning their own personal PC, and people thought, why not link them together, start communicating with those things, right? So that's when the internet was born, and the data started getting more and more every second. Things started exploding actually, and that's as a neighbor to that, you had this new thing coming in called the Internet of Things, wherein every device, irrespective of it being a computer or not, it started pushing the data, right? So these are the times when your data is actually leaping in petabytes, right? For example, if you consider the weather company, there's about about 3 terabytes of data streaming in for every 1.6 seconds. 3 terabytes of data per every 1.6 seconds that needs to be processed, crunched, so it can give us a small weather report that we obviously ignore because we don't care that much of weather reports in India, right? So that's the thing that started pushing humans and computers to get closer. The amount of data is exploding and the computation also started increasing parallelly with them. The power of computation became so intense, so big that it actually started making sense to use machine learning again. People revisited the idea of machine learning and then the next evolution is the cloud part, wherein everyone's now a developer. Everyone wants to develop something, but not everyone has all the resources that are needed, right? That's when you have these so-called cloud providers. What they did was they had a centralized resource center and they started allocating you with whatever resource you want and you temporarily pay for them and things go back, right? So if you consider these two parallel tracks wherein the infrastructure is actually given out by someone else and that someone else, the compute time or so-called compute time is actually being managed by someone else and everyone wants to get started with machine learning, right? So the next evolution would actually mean it's a very logical step to actually take machine learning and put it on the cloud, right? Machine learning is really compute intensive process and you also have people who are providing. So the next step would be put that service on top of machine learning. So, right, but one problem is the regular CPUs that we use every day are too slow. If you consider CPUs, right, the current execution rates, they are too slow for the increasing computation need by machine learning algorithms. These algorithms are increasing exponentially, but how many of you know what's Moore's law? Right? Moore's law is something that puts a limit on the transistor size, right? So if you can't decrease the transistor size, you can't increase the number of transistors in a processor and that actually limits the compute size, right? So that's with the regular architecture. You go with a regular architecture, your CPUs are getting hogged by these machine learning processes. It's too intense for them, they can't do it. Then we fortunately have an answer from the gaming industry, right? So gaming industry have been using something called parallelized processing, right? Any ideas onto what they are using? The regular GPUs, right? So they've been using these GPUs to actually enhance their bit rate and the frame output. And what we saw is that was exactly what we needed. And we took it and we started training machine learning models using GPUs in sync with CPUs, right? So if you usually go with the charts, right, probably the conversion format was, if you go with the charts, right, a regular GPU, a standard GPU is up to 45 times faster than a CPU, right? It's not ones or twice, it's 45 times faster than a regular CPU, right? So just when we cross that particular hurdle, right, hurdle of having something constraining that is limiting us from exploring the depths of machine learning, we just thought we had the holy grail. We have the machine learning algorithms, we had the data, we had the CPU, we bypassed that CPU limitation with GPUs, right? So people started thinking of something called the convergence or singularity, right? Singularity is when the knowledge becomes stagnant. There's a point after which there's nothing you can learn. So people actually started predicting 2012 as a singularity, right, wherein things are exhausted, things are saturated at that point, right? But something interesting happened when we took off all these limitations and still started running machine learning models with the data. The actual machine learning algorithms stop behaving the way that they are supposed to be. Even if there's increase in amount of data, when you come back to machine learning, right, everyone knows that data is oil. You have good data, you have a better machine learning model. You have bad data, there's a bad machine learning model, right? But after a point, the regular machine learning algorithms started behaving in a weird way that is not supposed to happen, right? Machine learning, even when there's an increase in the amount of data, the performance of the machine learning remained almost constant, right? So that's when people actually thought there's something wrong here and we need to look deeper inside, see why things are going bad. And that's how they gave rise to this one field called the deep learning, right? So deep learning is in which it's not that statistical, and it's more like a black box kind of thing, and things are working at a faster rate, right? So that's when we bring deep learning into this entire field of machine learning, right? So what happened when we got with all of these things, right? And the best part about open source is everyone's a developer and everyone can get access to whatever is leading or bleeding in the current technological field, right? So when that happened, the number of developers who are starting to explore things have increased drastically. Everyone wants compute time. After a point, why not make it easier? Why not just give you the compute time instead of giving you just the compute time? Why not give you a platform as a service wherein you can build your own stuff, right? So that was the next logical conclusion. And from there, something else came up, that is service as a service, right? So there are multiple ways of evolution that we as developers dictated the industry leaders to take from there, right? So we at IBM, what we did was we used the same opportunity to introduce something called machine learning as a service, right? In which, if you look at machine learning, it's basically something that is fixed, something that is more mathematical than something computation, right? So in machine learning, most of the algorithms and everything that you used are fixed, and it can be re-repeated, right? If you're starting with machine learning with scikit-learn, something as simple, all you had to do is learn two methods. For example, if you take k-nearest classifier, knn.fit and knn.predict. Fit creates a model and predict actually answers your questions. So when things are that constrained and things are that rigid in a format, we thought, why not take all of that and build it into blocks, right? This is basically what you're seeing is called as a data flow, wherein you decide how your data is going to flow through the entire machine learning model, right? You can start appending fields, you can start nullifying, you can start filtering out the null values, all the pre-processing steps, and then actually start creating a machine learning model, and in the end start evaluating, right? So things became this easy. So you don't actually have to be a mathematician to get started with machine learning. You just need to have the data, you need to know what you want to do, and a simple flowchart will take you there, right? The best part is we already have the GPUs and Power 9 systems, right? So what we did is we started running this entire stack on a Power 9 system. Basically, Power 9 system is a bit of improvement over the regular GPU, and it's IBM proprietary tech. So that's where we got 6.2 times faster than a regular GPU benchmark, right? So usually what happens is, even you're computing your machine learning models or a parallel processing unit or a GPU, there's still the CPU in the loop, and most of the critical operations should go through your CPU. And there's something called the bus, a bridge that connects or communicates between the GPUs and the CPUs. That standard bus is actually acting as a bottleneck. It's slowing down the flow of data. So what we did was we replaced that with some proprietary tech, and that's when we came up with Power 9 systems. Power 9 systems are up to 6 times faster on a standard TensorFlow benchmark test, right? So this entire stack runs on Power 9 systems, right? So all you had to do is select the input of data and reroute it through multiple nodes that take us to the final machine learning point and the evaluation point. Once you're done, you click on run and your model is created and hosted on Watson Machine Learning. And the best part about this is we are trying to make things as open source as possible, keeping things as developer friendly as possible. I mean, only then we'll be growing together, right? So there's an option called download on the top. If you click on download, you can actually download the entire notebook for this code, right? Whatever machine learning model you've created using flows can be downloaded with your favorite library, be it TensorFlow, Keras, Python, PyTorch, everything, right? So you directly download and you can run it everywhere. So this was what we did with machine learning, but what happened was the same thing. We saw that machine learning started working after a point, right? And then there came deep learning, this new field of computation that's even more compute intensive and even more harder for us to do. So what we thought was, we did it with machine learning, why not do it with deep learning, right? So we just tried to put the entire thing on the cloud and offer it as a service. But with deep learning, we face certain issues, right? You have too many things to manage, too much hardware, too much. For example, if I'm having a data center, there are tons of GPUs running and there are tons of CPUs running. Managing a CPU and GPU and making sure that which process needs to run on what is actually taking us a lot of time. But when you put in bulk of these things together, it gets even more harder, right? So things started getting really tense and failing a lot. So but then we think back and we saw we already solved this particular problem. We've been doing it all along since back from 2016 with something called the Kubernetes, right? The cluster management system, in which your resources and everything are actually being dynamically allocated rather than you statically trying to fix up something. So we thought this was the right answer, and that's what we did. So we actually deployed the Watson Watson Studio, the entire Watson Studio platform, using a Kubernetes engine, so that it is auto scalable, right? So whenever your model is running, and our systems find that it needs more of GPUs, or it can be better if you include a number of GPUs along with it. It asks you for a simple permission. Once it's done, it starts including the number of GPUs, right? So for the architecture nerds here, this is the architecture of whatever we are trying to do. This platform is, we named it as Fabric for Deep Learning, right? So this is the entire architecture, right? You have the regular cloud hardware sitting, the provision systems and the regular CPUs, and on top of that, you have a cluster of GPUs that are being managed and allocated dynamically by Kubernetes, right? On top of that comes our entire service stack, in which you have a Docker container running a, say, a Jupyter notebook or something of that sort, right? So then comes the entire stack, and the top is what you'll be seeing from your end. A simple interface where you actually write your code and start running it, and the runtime is everything beneath that layer is actually managed and provisioned automatically by our Kubernetes structure, right? So the thing, right, once we try and test out something, the one thing that we always believe on is metrics, right? So what we did is we performed some n number of standard tests using a regular conventional methods and using Fabric for deep learning. And the one thing that we found out was it was actually 2.5 times faster than any other conventional methods. And my slides are ruined, it's a different effect, right? So that's what we saw when we actually started deploying Kubernetes, actually deployed GPU access managed by Kubernetes as a service on the cloud, right? So like I said, the best part about all of this is open source and it can be accessed by anyone right away, right? So it's a simple GitHub link where you'll be taken through a series of steps that help you install things starting from a Kubernetes engine. I mean, it's for beginners and it's for everyone. You start installing it and you can try and test it out on your local PCs where you dynamically allocate multiple cubes, or you can actually run that on IBM Cloud for free, right? So when you're talking about IBM Cloud, we have a light offering in which it is free forever. You don't have to even put in your credit card. So I suggest just go through the GitHub repo, start trying to implement this entire architecture on IBM Cloud, right? So that's when you'll see the true power of computation. We also have some standard set of tests that you can quickly run and evaluate the performance of this entire architecture on the cloud itself, right? Thank you guys.